Great, wonderful, wonderful. So in the last discussion we were having that we were talking about whether we should learn about backpropagation or not. I think we should learn about backpropagation. Okay, so I discussed with other members in the team as well. So I think we will go into the entire loop of backpropagation because couple of reasons. One, I found that when I tried to explain this backpropagation to other teammates, I found that it's not that difficult a concept as it has been looking like. Second, second, of course, the rest of the sessions depend on it. So it's important that we know about backpropagation. All right, so let's get started. So, all right. So far, what we have learned is that if we kind of model our if we create kind of a hierarchical model of things, then we will get the better results. So okay, let me put it again. So if we create a multi-layer of neuron kind of a model whereby we have kind of multi-level of linear regression there along with some more functions, then it will be better. I'll just go back one more step. So here, so this is the kind of model that we have learned so far, that the multi-layer perceptron, this is the kind of model that we are going to work with in the rest of the things. So mm, researchers figured out that if we have like model our logic or our code in a way that it looks like this, then the outcome is better. The results are great. So what we do is generally we have these kind of layers, right? So this is input layer, this is hidden layer, this is the output layer. So here, each of these are resultant of basically these values. Okay, resultant of these values. This is what I'm going to walk you through. We'll take an example, a simple example, and try to work out the values. Okay, all right. So great. I'm going to start from really basics, and I'm sure that it won't take too much of time because all of you need kind of a little brush up. Okay, so here we go. So, all right. So, how many of you have learned differentiation earlier in the uh, school? Basics of differentiation. Okay. Okay. All right. So we are going to do a little brush up, and you will be amazed at the fact that whatever we learned long ago was a very important part for doing the predictions. That, and good news is that till now the till now most of the IT software and programming has not much relationship with the mathematics that we studied earlier. But now, after the machine learning and data science has come into play, whatever we learned uh, in earlier in the school, that is playing a very important role, that is coming back and being used. So there was this t-shirt which says that sin x cos x and dy by dx and things like that. I'm still figuring out that where do I put them to use. So my answer is that there was this t-shirt of somebody I saw in one which this was written. So my answer was that why don't you try to do predictions and you will be putting everything to use. All right. All right. So this is where we are, and I'll start from really basic. So let us say there is y and there is x, right? So y is a dependent variable, and we say that y is x square, right? So the way we define y is by the way of this. Okay, should I pull out the sketch? Let me pull out the sketch. Okay, James, are you comfortable with the little bit of differentiation and maths? If not, let me just walk you through it. Okay, so let us say there is a variable y which is equal to x square, right? So when we say dy by dx equals, actually this is 2 into x. How do we know that? Because we memorized it. Okay, and the derivation is very simple. So the derivation is that um, this is equal to x plus delta x square minus x square divided by delta x. So basically, what does it mean? What does it mean? Again, this is a very important point. So dy by dx means the rate of change of y with respect to the x. Okay, rate of change of y with respect to the x, meaning how much is y changing when we change a little bit of x. How much is y changing when we change a little bit of x, right? If y is the distance and x is the time, so we have change of distance by per time. This is change of distance per time is, anybody? Change of distance per little change of time, the rate of change of distance with respect to time, velocity or speed. Correct. If the distance is a vector which has the direction, then it is the velocity, and if distance is single direction, it is the it has no direction, then it is the speed. Good, very good, right? And change of speed with respect to time is, so so acceleration, that's right. Great. So if we know how somebody's speed is changing if somebody's distance is changing with time, we can compute its rate of change with its we can compute its velocity at any time, we can predict its acceleration at any time, and so on, right? So differentiation is a great concept because it works on the idea of slight change. Okay, so how did we compute this like to x square, the differential of x square with respect to x is 2x. How did we compute? Basically this way. And when we expand it, it is essentially something like x square plus delta x square plus 2 of delta x into x and minus x square, right? Divided by delta x. Wonderful. So this expression basically means that we cancel out these two terms and then we basically divide by delta x and we get 2x plus delta x, correct? So, and this term is negligible. So the dy by dx, is 2x, right? Here there is a condition that I'm not writing the condition that delta x is tending to 0, right? So we are taking tiny amount. So what does this expression mean? This expression means that we change a bit of x by the tiny amount called delta x, and then we observe the change in y. So this is what this expression means, that how much per change in delta in x will there be a change in y. Okay, that's what we have computed. And since this change is really tiny, so this fraction we are marking as 0. Okay, therefore dy by dx is 2x. All right, so I hope this is clear to everybody. Now there is a tiny extension to it. The tiny extension is, what if we have y equals sine of x and the square of it. What if we have this? So what will be the dy by dx? Okay, what will be the dy by dx? Yes, so this is where the product rule comes into play. Okay, so what we do is we express this in the form of y equals z square, right? And where z is equal to, say, sine of x, right? So first we compute, in order to compute this, what we do is we first compute dy by dz, right? Which is, anybody? How much is this? Dy by dz? Correct. This is 2z, right? The way we did in the previous step. Similarly, people found that if we differentiate sine x, the answer is cos x. If we differentiate sine x, the answer is cos x. And how did we do that? How did they do that? By using the same mechanism, like x plus delta x minus sine x plus delta x minus sine of x divided by delta x tending to 0. And then they did the expansion of this one and found that it's actually cos x. Okay, so basically it is that same mechanism that has been followed. So here now dz by dx, meaning what is the rate of change of z with respect to x? How much is that? It is, my handwriting is little bad, not little, actually quite bad. Okay, so we have dy by dz and dz by dx. So this is 2 into z and this is cos x, right? So so what people found out that we can express dy by dz as d dy by dx, rate of change of y with respect to x, as dy by dz into dz by dx. Okay, so right, so this is how it looks like. So basically, if we put y, as in we put a variable here, y equals z square and z equals to sine x. So rate of change of y with respect to x is equal to, first, this part multiplied by this part. Okay, so this is 2z and z is how much? Sine x, correct? And into cos x. All right, so yes, it is sine 2x. Great. Is everybody with me so far? So this is called the chain rule. This is called the chain rule. Okay, so in very simple words, if if we know that, okay, so let's get back to next level now. Okay, so imagine that we have written a function, right? In Python, let's say we have written a function. This is my function. It takes x and it does something in it, correct? it does something in it, right? So we give it an output and it does something. So it takes, let's say, Z, and okay, so I'll again put it back. So let's say we have y equals function of Z, which is taking some value. Okay, so we know that y is a function of Z, and Z is a function of x. Okay, so let's say these are the let's say this f, instead of f it is g. Let's say somebody has defined these two functions f and g um, in Python, and we would like to find out how much y is changing when we change a bit of x. How much y is changing when we change a bit of x, right? So all we do is we basically apply the chain rules. Okay. A question from Shiva is that how do we derive the differentiation of sin x? So okay, that's a good question. Okay, let me also try to recollect. Okay, all right. Let me just save it. Okay, and here. Okay, where did it go? Okay, just give me a second. I have to turn off some of the windows. Just give me a second. I'm trying to turn off my windows, some of my windows, so that my Mac doesn't make so much of sound. Wonderful. So where were we? We were on the sketch. Okay. So question was that, okay, I'll come back to this one. Let me try to answer the other question. Other question is, what is the, if we have y equals sin x, how do we compute dy by dx, right? Okay, so it'll take me some time. I think I've also forgotten. Sine of x plus delta x minus sine of x and whole divided by dx. Okay, any suggestions, anyone? So okay, so this is all right. Mhm. Okay, probably one thing we could do here is all right, probably one thing we could do here is basically do the expansion of the series, right? We could do the expansion of series, and expansion of series is all right. Okay. Okay. So yes, that's a good idea. All right. All right. I think, yeah. Thank you so much, Pratik. Yeah. I think Pratik still remembers it. So basically we do sin A plus B expansion here, and sin x cos dx, right? And plus this, so which will turn out to be this, and we can ignore these delta x parts, and no, not delta x part. this will be cancelled with the other part, and we'll be left with only cos x. Okay, so something like so. Sine A plus B is this. All right, so that's right. Okay, so great. All right, wonderful, wonderful. So which one was it? Out of these, we did not save. This one is done. This okay. Yeah. All right. So I hope that's clear. Thank you, Pratik, and I hope that's clear. Now coming back to it. So when in the computing also we apply the similar principles or same principles actually in order to train our mm, a neural network. So we'll be applying the chain rule in order to get the backpropagation done. All right. So all of whatever we are learning, it's going to come back to the use, and we are going to learn. Okay. Question from Binta is: could you have some material for someone who need to review the basic maths, and focus on deep learning? Sure. Okay. Sure. Actually, I thought that it'll be useful for all, and so I'm sure it'll be useful. So let it be with me. And here, so we're talking about in the same mechanism here, the rate of change of y with respect to the rate of change of x is what we are looking for, correct? So again, we'll apply the same principle. We'll differentiate z with respect to x, and so same thing we'll apply here. Rate of change of y with respect to x is going to be f, and the other way of writing df by dz is by putting a dash over here. Okay, so all right, so this is how it's going to be. So this is dz by this. Okay, so basically it's the same chain rule applied again. And now the second part I would like to explain is the with respect to the main equation. Good. All right. So far, what we learned is the basics of maths. And now coming back to, right. All right. So here we go. And I'm going to keep this ready. I'll just take this from here. All right. So, okay, select all of these. All right. Okay. Or I'll just draw it again. Great. All right, so today what we are going to do is we are going to create our really basic network, and we would try to predict or try to do the gradient descent on that. All right, now let me again go back to the basics. Okay, so imagine that you had some input and you have some output, right? And you what you decide is, let's say your input is X, and let's say X is Y, your output predicted is say 5. Okay, so we have similarly other values of X for which we are given the values of Y, and what we want to do is we want to figure out what is the relationship between Y and X. Okay, so there is a huge black box here. We don't know how we're reaching to Y. Correct, we don't know how we are reaching to y based on x, but we are giving so many of x values that uh, that if we have enough of x values, and we can come up with a model that on what basis y is being computed from x. Let us say there is a machinery, big machinery, okay, big machinery here, right? It is giving out y, and it is we are inputting x. So, so given x, we want to predict what will this machinery give as the output, right? That's what the machine learning was all about. That was the whole supervised learning was all about. That when we give this input, and we are given these inputs, and we are told that for these inputs we got this output, what will be the output given the input, right? Given some unknown input. Okay, whether we call it extrapolation, whether we call it interpolation, but it is basically the prediction of value, right? And this prediction of value is something that is common to to the way to the way human brain works, as well as most of the mathematics was designed for prediction of the values. Doing the basically that's how most of the maths have been oriented towards, right? So some of the things that we learned was so far was that maybe we can express y in terms of x in, say, a linear expression way. Maybe we can say that y is some multiple of x added by some constant, right? That was the linear regression. Now, when we talk about some of the researchers, the neural networks, they figured out that if we create kind of layers of neurons, and each neuron is basically uh, combining the inputs and giving the outputs, then we should get the results. So let me just try to draw a really simple model. Let's say one of the models we come up with is like really simple. I'm going to go really simple here. Okay, so let's say this is a very simple model, and how much layer? Okay, so this is our input. Okay, this is our input, this is our output, and there was one more here. Or I'll just, okay. Okay, just give me a second. Ouch. I think drawing my own will be better. I don't think it makes any sense right now. All right. So let me just try it again. I'm really sorry for this. Okay. So imagine that we have two layers of it, and I'll just put it on this corner. Okay. Okay. Now, so this is our input, right? And x equals to 1. And here, this is our output. Let's say y 5. Okay, so instead of saying that instead of assuming that y is equal to mx plus c, we are saying that it is somewhere related like this model. Okay, so this is our input, and let's say there is one layer in between. Okay, all right, and we are saying that there is in between the layer, and we call it h, hidden layer 1. Okay, and this is, let's say, our output layer. Okay, so something like this. Now, there is we generally, the way the model is expressed is that we put it, how do you move this stuff? Okay, so like this. And okay, so all right. Now I'll explain to you what are these meant for. Okay, so this one is for basically the bias. Okay, just exactly like linear regression. All right. Now, so here what we have is we came up with this idea that let's put it in two layers. So here there are some weights, let's say W11 and W12. Okay, and here W21 and W22. Good. So we say that let's create this, and we express h1 equals h1 equals w11 into x plus 1. Okay, generally we call this x1, but for now let's just keep it this way. Okay, and o1 equals h1 into w21 plus not 1 here, it is going to be 1 into W12. And W22. Okay. Generally, what happens is in the perceptron model or any neural network, what we do is after this here, we generally put a step function, right? Generally, we put a step function here at this point of time, but for simplicity's sake, we are not putting that step function because we want to do this computation manually. Only then we all will get hang of it. Okay, so the perceptron model basically says that there is after this step whereby we are expressing this result in terms of multiples of the input plus a constant, right? Plus another constant. So that we are letting go of the basically the step function for now. We will come back to that again just to simplify things a little bit more. We have come up with this now. So this is clear, right? So what we are going to say is we're going to do in this is we want to find out these values of the weights, W11, W12, W21, W22. We want to find out these weights such that this output is almost closer to Y. We want to find out these weights such that the output is very close to the Y. Okay. So in the beginning, what we are going to do is we are going to start with, in the backpropagation mechanism, what we do is we start with some random values of W, compute H1, then we compute O1. That's called the forward pass, whereby we compute these values, right? Once we have computed the O1, right? O1 will depend on H1 and 1, and we will assume these values. Okay, and H1 we have computed in the previous calculation, which is equal to this, multiply this, and this. These are assumed values. So we, in the forward pass, we will compute the value of O1, right? And we will compute the error on the O1. We will compute the error by subtracting O1 and Y. That is our error. Now, at this point of time, we'll check whether this error is negligible. If it is negligible, then we stop and say that, okay, we have found those weights which are doing really good, and let's stop, right? If not, then we are going to go back. We're going to go back and try to tweak these weights. And how do we tweak these weights? Okay, one thing is we could just randomly go scan through all kinds of weights, all kinds of values of W, and then move ahead, right? The other way is the gradient descent way. Okay, the gradient descent way. And how does that work? So, let's just go back one more tiny little step and give you a quick idea, okay, about the gradient descent, or should I do it in midway? I'll do it in midway when we, okay. So all right, all of you have to help me with this. So imagine that the values of weights we are putting in initially is 1 each. Generally we keep them between 0 to 1, but we'll discuss that later. I want to simplify the calculations. So initial assumed values of W are 1 each, okay, and X we know, and H will compute. So H1 is going to be how much? H1 is how much? Quickly, 1 into, or okay, let me just tweak. Okay, I think the values, let me just change them a bit. So X is say 2, W is say 2, and this is say 3, and this is say 4, right? Then it'll make more sense. Otherwise the results will look too ugly. Okay, so H1 is going to be X into W11, which is which is 2 into 1 plus, please help me in calculation, all of you. Okay, so H1 is 2 into 1. Okay, so H1 is 2 into 1 plus 2 into 1, correct? 2, you can say 1 into 2. This is 4. So H1 that has come out is equal to 4. Perfect. Now, the O1 equals, yes. So O1 equals this 3 into 4 plus 4, correct? Which is 16, right? So let's just put it 16. So do you think there is an error? So this is the expected value and this is the actual value. Yes. So therefore, we need to go back and try to change our weights. And how do we change weights? The way we change weights is in the normal, the usual regression we do is, let's say we have, right? So what we do is we compute the error and we subtract something by the rate of error. We subtract the weights by rate of error. Now, this was right. This is what we learned. I'll just draw it once. So whatever weight it is, right? Let's say we have W11, right? So W11's new value is going to be W11 minus eta. Eta is some learning curve into rate of change of error with respect to rate of change of with respect to W11. Okay, all right. So what is it that we're talking about? Okay, so in the earlier, what we understood is that we need to change the weights. We need to change these weights. We could actually just ignore the error part and just try other combination of weights. We could just randomly try to scan through all the variables of weights, but that would not give us great results, right? Because it'll take long time. So instead, what we do is we try to change weight. We try to change the error. We try to change weight. We try to change weight in the direction where the error is minimum, right? So what we do is we so what we do is we observe that how is our error dependent on our W. Okay, so imagine that our error, right? This is our error and it is dependent on our W like this, right? And let's say it is like this. Okay, so if our error is dependent on W like this, what we can do is we can, let's say for a particular value of W's, we find that the error is the error is changing in this way, meaning when we increase W, the error is coming down. The error is coming down because of the slope. If we change W, the error is coming down. This is essentially the dE by d of W11, the rate of change of error with respect to the W11. That's what is the slope. So what we do is, instead of whether it's so let's say we had just we were subtracting some value from W. What will happen is, instead of considering this part, so if we had just only up to eta, what will happen is that no matter how much is the slope, we are not moving fast. But in this case, why this formula is, again, this is basically what we discussed in the gradient descent. So why are we using this formula? We are using this formula so that we can reach to the weights really, really quickly. How? By going into that direction, where the error is going to be minimum. So we are at this point and we observe that error is really changing fast, or error is decreasing because of W increasing, right? Error is decreasing because of increasing W, and therefore we basically multiply it with the rate of change of error. Okay, so we subtract our weight, we subtract, or let me just put it this way. Okay, imagine we were here, right? This is a positive slope. This is a, okay, sorry. So imagine we were here. This is again the slope, let's say at this point. So this is a positive slope. Okay, so we have some value assumed for W, and we would like to, which direction we would like to go if we are here, right? Well, let's say we are here. For this W, we find that error is this much, and the rate of change of error is actually positive. This is positive, this is negative, all right? This is positive. Okay, so what we'll do is we'll try to go in this direction, of course, right? We would like to decrease W, because decreasing W is decreasing E in this case, correct? So we'll do that. All right, so although the diagram is a bit different, and uh, so coming back to the point that this formula, I hope everybody is clear why this formula is like this. Yes, is everybody clear about this formula? Okay, so if anybody wants me to explain again every part of it, I can explain again. Why do we have eta? Why are we subtracting it? Why is there a rate of change like this? And why is this factor at all? Okay, so we could have done, right? So I can explain every part of it, because we're going to use this multiple times. So we are going to combine this with our chain rule. We call that chain rule, whereby the one that we described earlier. So we're going to combine this with the chain rule in order to come up with the values. Okay, so all right, is everybody okay with this? Question from Vinta is, why do we have to select the values of these biases as one always? So could we choose other values to the biases, such as integer or float? Yes, of course you can. Okay, yeah, so it is like saying that, right, this is a good point, right? So let's say when we say y is a function of x, correct? Let's say we say y is a function of x, right? Or y is a function of x. It could be anything, right? It could be anything. this function f could be anything. So one of the functions is, we say, maybe there is a linear connection between the y and x, right? Meaning it's like linear line y and x. So it is like linear line. Now there could be many lines. It could be this line, it could be this line, and so on, right? We don't know. So we got, even if we say that okay, there's a linear relationship between y and x, still there is since even if we say that it's a linear relation, still there are two parameters. One, what is the slope of this line, and how far it is from the center. How far it is from the center is c. So mx plus c, right? Now question from Bintao is why we are taking that as one, because we want to, it is really easy if we kind of express it in this way, right? This is x, 1 and x, and this is m and c. Okay, so basically, since we need to find the value of c, right, as well as the value of m, therefore it's easy to express it this way. Okay, therefore we generally put 1 here, and sorry, this is going to be, this is c. Okay, actually this is supposed to be c. Okay, and this is supposed to be m. Okay, so when we express it like a matrix, it becomes really easy. All right, if we say take some, let's say, constant here, then let's we say take some constant, then again it's going to be the same thing. Okay, we could actually take some other constant here. Again, this value that we are trying to predict is going to be a little different. Okay, so I hope that is clear. Yes, Vidya was able to explain. Okay, yeah. All right, I'm going to, yeah. Where did it go? Yeah, we were here. So any doubts about this equation, right? All right, is the one that we just talked about, the equation, how we are going to change w's, that was the one that we're going to use further. All right, now the next step is, so we found that okay, output that we have computed is 16. It was supposed to be 5. That means there's something wrong with these, right? So we start going back. Okay, so what we do next is, since we want to tweak these weights, we want to find out how is our error varying with respect to weights. Okay, so how much is our error? Generally, the way we compute error is by the way of doing mean square error. And how much is the error? 16 minus 5 and the square of it. Okay, and this is something. Okay, so this is the way we compute our error. So this is going to be 11 square 1 to 1. Great. All right, so although this value doesn't matter right now, this is the error that we have. Okay, or let me put it correctly. We say o1 minus y square. Okay, so this is the error we have, okay, in this. Now what we are planning to do is we want to find out how these weights are impacting this error, how these weights are impacting this error. And how do we find out that? Pretty simple. So first of all, we want to find out how is error being impacted by output. How much is that? So we say dE by dO1. Okay, how much is that quickly? How much is this? Okay, so dE by dO1. O1 is equal to rate of change of this O1 is 2 into, like this equation right here. So if we differentiate this with respect to O1, we will get what? 2 into O1 minus y. All right. So how much is this? 2 into 16 minus 5. Okay, which is which is 22, right? Okay, is this clear to everybody? So we just computed the rate of change of error with respect to O1, right? Now, the next thing we want to do is what is the rate of change of O1 with respect to W21? Okay, so this is what we're going to do. And how much is that? When we differentiate this equation with respect to W21, we get H1. Okay, so whatever concept that we just learned, we are reusing them to solve this complex neural network, right? We're trying to find out the values of those weights such that our output is minimum. So we want to go into the direction where we want to change those weights in a way that our overall error is minimized. How we are going to do that? By finding the rate of change of error with respect to each weight, and we will use the chain rule to find that. Okay, now you can see that we have clearly computed. And how much is the h1? H1 is 4, right? So now my question to you is, how much is this? How much is the rate of change of error with respect to W21? If anybody is not comfortable as of now, I can explain again anything. Okay, so, right, great, great. So this is basically the multiple of the two, right? Just the way we explained earlier. So, this is equal to multiplication of these two values, right? Good. So this is what we have here. So we have, all right. So the rate of change of error with respect to W21 is actually positive. That means that we need to decrease the W2. Okay, we need to decrease the W2. And how much will that be? So W21 equals to the previous value of W21 minus eta. Eta, let's assume to be, say, little tiny number. Okay, little tiny number. It's just any constant. And since the rate of change is generally high, very high, so we generally start with 0.01 kind of eta. Okay, although eta is, or learning rate, or this constant that we're putting here, is a hyperparameter, and we generally iterate over these learning rates. Okay, so here we are saying rate of change of rate of change of E with respect to rate of change with respect to W2. So what we are trying to do is, how much is it? So we are saying that decrease this weight in proportional to the increase in the error. Decrease this weight in proportional to the rate of change of error with respect to this. Okay, so the velocity of error needs to be subtracted. You can say, I mean, rate of change is kind of, you can think of it velocity. So that's what we are trying to do here. And now how much will that be? Yes. So question from Siva is, do we start adjusting weights backwards? Yes. So why are we doing that again? See, we know the rate of change of error with respect to O1. We know the rate of change of O1 with respect to this. We know the rate of change of this with respect to this, right? And similarly, we will know later on rate of change of this with respect to this, and hence so we can compute the rate of change of these weights with respect to E only if we know these parts, right? Chain rule. So we are applying chain rule backwards, right? The way in order to compute the rate of change of this, we needed two expressions. One, rate of change of this one, and rate of change of this one. So we needed these two expressions. Similarly, we need a third expression later, that how much is our H1 changing with respect to it. Okay. And also how much is O1 changing with respect to H1, and so on. Okay. All right. So how much is this? W21, which is 3 minus 0.01 into 88. Okay, so it is going to be 2.12. Great, great. So far, everybody comfortable? Now, similarly, we will have the expression for the second part. We'll say rate of change of error with respect to second variable is equal to rate of change of error with respect to O1 and rate of change with respect to the second one. Okay, and it's not definitely this. Okay, so how much is this? So it is equal to, this is fixed that we know, and this one is rate of change of O1 with respect to W22. It is 1, correct? This portion is going to be 1. Let me just actually write it separately. So rate of change of O1 with respect to rate of change of W22, rate of change of O1 with respect to W22 is 1. Okay, and therefore this value is going to be how much? All right, this value is going to be 22. Perfect. Okay, thank you, Vinta. Right, great. Great. All of you, please participate with me in this. This will help you, and this will help all of us. Okay. All right. It's okay to be wrong, but it's not okay to be not participating. Okay. All right. So to participate. So here, I hope everybody is clear about why this rate of change of O1 with respect to W21. Okay. Okay, good question. Question from Gigi is that how did we get one? So when we differentiate this equation, right? So O1 equals H1 into W21 plus W22. When we are differentiating O1 with respect to the second weight, these parts are considered constant, and therefore the differential of y equals to x, right, is 1, correct? So this is 1. Okay, or you can say that if there is a straight line and you differentiate it, the slope of this line is constant, and that's 1, right? The slope of a line y equals to x is 1. Okay, or in other words, if y will change equal to x, the rate of change of y will always be equal to whatever change you do in x. All right, so it's actually interesting to you know look at the differential calculus again, and all right, and move ahead. So great. So we now computed what? We computed the rate of change of W21 as well as W22, right? Now W22, the new value of W22 is going to be, anybody? W22 minus same eta, we are keeping the same fixed rate, okay, multiplied by multiplied by multiplied by rate of change of error with respect to W22. Okay, how much is that? It is, okay, I'm relying on Bintao. I'm not computing myself, but anyway, I can put it. So W22 was 4 minus 0.01 into 22. Okay, so which is 3.78. Great. So we computed some values here. Okay, so we can see that we are able to compute the next values of these. Okay, so the value of W2, both of these have been decreased a bit. Like this one has become 2.12, this one has become 3.78. Okay, now in the similar fashion, we're going to go further one more step. Okay, we're going to go further one more step, and now is the turn of these parts. Okay, so rate of change of error with respect to W11, with respect to W11, how much is that? It's going to be rate of change of error with respect to O1 multiplied by rate of change of error O1 by rate of change of okay, W11. Now further we could actually convert it into something like this. Okay, rate of change of H1 by rate dW11. Okay, so we compute the rate of change of error with respect to O1, rate of change of O1 with respect to H1, rate of change of H1 with respect to W11. Okay, so H1 is how much? H1 is this, right? When we differentiate this with respect to the W11, we get X, right? So here, let's just help me in this computation. Rate of change of error with respect to O1 is 22. So you can see that whatever we computed earlier is getting into use, right? Okay, this one though, this part, rate of change of O1 with respect to H1 is not something we have computed so far. Okay, so but dE by O1, once computed, it is being used multiple times. Okay, that's why we call it backpropagation, because we go from right to left so that we can utilize what we calculated in the previous steps. All right, now because in the real neural network there is extra function here, so there is extra chain here as well as here, right? There's a step function involved. Therefore it becomes more and more important to have to carry the what we computed previously. Just like in dynamic programming we retain, or just like caching we retain the previous values. In the same way we do this so that we can learn from, we can basically avoid a lot of computation. Okay, so who is helping me with this? So dE by O1 is 22, dO1 by H1, dO1 by H1 is how much? W22, correct? So this, when we differentiate O1 with respect to say H1, it'll be W21. W21 is how much? 4. Remember, we are not going to utilize these values until the entire pass is over. Okay, we are not going to utilize these new values of W21 until the entire pass is over. Therefore, we are going to just stay with the initial values until we compute till here all the values. Okay, therefore when we differentiate this equation with respect to H1, we get W21. W21 is 3, not 2, sorry. Thank you so much, Gigi. That means all of you are paying attention. So okay, great. Now dO1 by H1. Now dH1 by dW1. dH1 by dW1 is equal to x, right? When we differentiate this equation, we get x. Therefore, it is 2. So the value of this is how much? Okay, great. Wonderful. Wonderful. Thank you so much. And let's, okay. So let me just try to, all right. So I hope this is clear to all of us. Now, the value of W11 is equal to W11 minus eta, right? Into dE into say 132, or we can just write dE by dW11. This is equal to, what was the value of W11? 1 grade 0.01 into 132. So this is equal to minus 0.32. Thank you, Bintao. Wonderful. So we get the new values of W1. Okay, these expressions look so crazy because we are not so tuned to working with the equations for so long, but these are actually really easy. If you break it entire thing into parts, then everything will look really simple to you. Okay, now the same thing we can apply for the second weight, right? So the rate of change of error with respect to W12 is rate of change of error with respect to O1, right? Rate of change of error with respect to O1, O1 with respect to H1, H1 with respect to W2, correct? So the only thing we need to change is the last step in this, W12, correct? So now so you can see that the things that we previously computed are being used, and that's how we generally avoid a lot of computation. Okay, okay. So those, okay, so here dH by dW, okay, W12, that is 1, correct? So it is, that's right, this is 66. This is right. So great. Now this W12, okay, I'm just going to change it a bit, and this, and we have, all right, so how much it is, anybody? 1.34. 1.34. Okay, so this is how we computed the newer values of weights. Okay, so it is very clear. So you can see that this W, we started with 1, it is further reduced to uh, it became negative actually, minus 0.32, and W12 became this, and W22 became this, W21 became this, and so on, right? So we can recompute our values with this. Okay, so H1 is equal to W11 minus 0.32 plus into 2 plus 1.3234. Okay, I can actually use Python for this. Okay, oh, this one is Python 3, so I'll actually I'll just use my CloudxLab one. Okay, I could say source activate, in case you guys use Python from the console in CloudxLab, you could use this command to activate the environment of Python 3. Okay. All right. So this is zero point 0.7, right? Is this 0.7? All right. Now the O1 equals how much? O1 equals W21. What was W21? 2.12 into H1.7 plus W22 3.78. All right. Okay. So generally what happens is here at this point we pick up the next values and then do the batch. Okay. So how much is this error? 3 point. Okay. So W22 is this correct? Did we decrease the error or increase the error? Wow. This is good. So you can see that we are quite close. So in a single shot, we were able to reach to this point, right? From 16, we have reached to 5.26. Okay, just by simple calculations, right? So you can see that this approach is far more efficient than just iteration, just normal iteration. So all we do is we compute the rate of change of error against each variable, how each variable is impacting the error, in what direction, whether it's increasing the error, whether it's decreasing the error, and so on. So that's why so when we are computing the error, we compute the rate of changes of all the functions. Therefore, all these functions that we are using here should be differentiable. We should be able to differentiate them uh, and easily. Okay, that's why we will see further why we are using some functions. Also note that we have not used any activation function, because activation function will bring its own complexity here. Activation function, what it does, it basically brings non-linearity into this game, into this linear regression. What we just did, it's basically what we just did was like two-layered linear regression, right? Linear regression is basically trying to fit a line into the data, right? So this is what the backpropagation is about. All right. So this is how the backpropagation happens. So we basically keep on going back iterations like multiple passes. And also please note that here, right now we took one value of X and one value of Y. But in reality, we have thousands of values of X and thousands of values of Y. And at every point when we are computing these values, we average out the error with respect to all of the values of X. Okay, we average out, we, so again, there are, so in a real network, what are the things that change? Okay, let me just tell you. Okay, so one is the number of features that we see here. There are going to be more features first. Second, second, okay, so first thing is more features. Okay, more features. As in, there'll be X1, X2, X3, and so on. So there are going to be multiple features, right? For each feature, we create an input circle here. Okay, remember that this is basically the feature. If we have a table of data, like pixels, right? First pixel here, second pixel here, third pixel here, fourth pixel here, like that. For each image will be an X, and here each circle is going to be the pixels value. if we are going to say predict the image, we are going to predict the image. So this what you see here, these circles here, they're going to be say 784 circles, okay, in case of MNIST data, right? And there are going to be many such images, right? Many such images, okay, many instances, right? Third thing is, it's every step here is going to have one step function or activation function. Okay, activation function. We have avoided activation function because we wanted to learn things stepwise. There were many concepts that we learned. We learned the basic differential calculus. Where does it come from? Its significance. We also learned learned the chain rule. We learned the gradient descent. We learned how the back propagation based on all of these concepts. So there are multiple concepts included here. There are other tiny concepts like dynamic programming. How many of you are aware of dynamic programming? Nobody? Okay, okay, okay. So the easiest way to think of dynamic programming is basically caching. Okay, so what we are doing actually here is we are remembering the values that we computed in previous steps and reutilizing them. Okay, reutilizing them so that you don't have to recompute them, so that we don't have to recompute them. That's what is mostly the dynamic programming about. Dynamic programming is about remembering the past and utilizing those values. Okay, so instead of recomputing them, if recomputation is too heavy, we just cache it. It's that way. Okay, now these were the assumptions that we made here. Okay, these were the simplifications that we brought, basically the basic features, many instances, activation function. So in order to reduce the complexity of this discussion, we kept these things really simple. So if there are more features, then this equation will look like w1x1 plus w2x w11x1 plus w12x2 plus w3. So this equation will increase, right? This more parameters will be there. More features means more of these, right? And this h, right? If there are many instances, this h will be computed for each instance. There'll be h1, h2, h3, h4, and so on. There'll be this. Okay, and okay, so here, okay, there are going to be many layers. Okay, there are going to be many layers, and there are going to be more neurons here. Okay, right now their activation function is not there. Activation function is missing. So I'll explain what is activation function probably here. Okay, so remember we did this discussion where we are given value of x1, y1, and we were recomputing the value of say this, and then applying the step function. Okay, applying the step function. So coming back, and yeah, here. So here, I hope you remember. So in the perceptron model, we have one. The Z is computed by all the input vectors, like input features, like W1, X1, W2, and so on. And then we apply a step function on top of this value, right? So this is here we are using step function, but in general in the MLB we call it activation function. It could be sigmoid function. It could be there could be many other activation functions. Okay, so this step function is what we have avoided in this backpropagation model to keep the discussion really simple. All right. So correct. So activation function is nothing but something that converts the values to between 0 and 1, right? We apply that function generally in such a way that it brings down the value to 0 and 1. Also, the role of activation function, I think that we'll discuss again. All right. All right. So what we learned so far is that for each training instance, the algorithm feeds it to the network and computes the output of every neuron in each consecutive layer. This is called forward pass, just like when making predictions. Then it measures the network's output error, the difference between the desired output and the actual error. Then it computes how much each neuron in the last hidden layer. So how much is this error contributed by all of these edges, right? All of these, the previous layer. And then it proceeds to measure how much of these error came from the previous layer until we reach the input layer. The last step in the backpropagation is gradient descent, basically changing the weights in proportion to the error contributed by each weight, right? And 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 that's what we did. I think this whole text will make sense now. Is it making sense to you, this text? The last step of the backpropagation algorithm is a gradient descent step on all the connection weights in the network using the error gradient measured earlier. Okay, so the reverse pass efficiently measures the error gradient across all the connection weights in the network by propagating the error gradient backwards in the error. Hence, the name of the algorithm is backpropagation. Okay, so these were the things that we did. We did forward pass for each training instance. The backpropagation algorithm first makes the predictions, right? Then we measured the error. Okay, then we measured the error. So we computed the error at this point, right? Then we did a reverse pass, right? Then goes until each layer we measure error contribution from each connection. That's what took the entire of this time till here, right? And then we finally do the gradient descent. So basically these parts, while we computed in parallel whenever we were computing, but it is generally done at the end. That doesn't make any difference. Okay, this is just to ensure that we don't change the value of weights in between. Okay, this and these parts are done later. Okay, just to make sure that we don't start reusing these values ahead. Okay, therefore the gradient descent step is done at the last. All right, so Balaji, Bintao, Gigi, James, Pavan, Pratik, Ross, Shiva, does it make sense to you? Okay, great, great. A question from Minta is, how many error backpropagation do we have to take, which should depend on the required predict value? Okay, how many error backpropagation do we have to take? Okay, question is then where do we stop? Is that your question? Yeah. So yes, just like in the gradient descent, we we do the early stopping. Okay, one way is that you keep on iterating until the error starts increasing. Okay, the moment error starts increasing 3 times consecutively, we stop. Okay, that's one way called early stopping. And we will talk about these parts very soon. We are going to go more into hyperparameter optimization of backpropagation after this. Okay, so we will learn those parts, and that's a very good, very important question that I would like to answer in detail. Okay, so I'll again come back to the question is, can we make error zero? Good question. But then there's always a fear of overfitting. Okay. So if you try to make error zero, first, it is really hard. Second, there are chance of overfitting. Therefore, we just take a tolerance based on our need. Okay, based on certain like fraction of the total. All right. So what we're going to do next is we're going to design the same backpropagation in TensorFlow, and then we will do the hyperparameter optimization. Okay, wonderful. So great. Now, so in the neural network earlier, the MLP, the multi-layer perceptron model, we were using something called step function. What was step function doing? Step function was like, if something is less than zero, make it zero. If something is greater than zero, make it one. That was step function. So step function contains only flat segments. So there is no gradient to work with. So gradient descent cannot move on the flat surface. So because if you compute the rate of change of error against a variable on which we have applied a formula which is like step function, the gradient descent will either be zero. It'll be basically the gradient will be always zero. Therefore, it does not make sense to use step function in the back propagation if we are going to use this gradient descent method. Right, right. Imagine that you like we talked about that you are blindfolded on terrain, mountainous terrain. That works fine, right? We can just judge the slope. But if you are in the city, if you are in the city and you are blindfolded, and the whole road is completely flat, and suddenly there is a gutter somewhere, right? And you're blindfolded and you're just trying to walk to the direction where there is uh, um, the slope is lesser. So the chances are that you might fall into the gutter because gutter appears suddenly on the flat surface. So you may not be able to basically judge the depth by the slope, right? The same case is with the step function, that since the step function does not have a slope, therefore the rate of change the rate of change is going to be zero, and therefore we won't be able to change the weights, and our weights will remain the same and it wouldn't work. Okay, it wouldn't work. So therefore, there was a slight change in the MLP. The multi-layer perceptron model, we had to make a little change, and the change was, instead of using the normal step function, we came up with something called a sigmoid function. Sigmoid function. So the key change to MLP architecture was made, and the step function was replaced with a logistic function. Okay, what is this function? 1 by 1 plus e to the power, e is nothing but a constant, 2.3 something, to the power minus z. Okay, so basically this value is going to be really small if z is very high, right? This value is going to be really small if z is very high, and this value is going to be really huge if z is um, z is huge. Okay, and now, so this value is going to be very close to 1 if this is 0, this is close to 0. This value is going to be close to 0 if this is this is really huge. Okay, so basically for a tiny change in z, this one swings to to really huge value or really tiny value. This change in z, and therefore basically this brings it down, this whole value, to between 0 to 1. Okay, so therefore if we change the sigmoid function, right, to something which is differentiable and has a slope, then gradient descent works really well, right? If you are right, if you, since your error is going to be depending on this, and hence the rate of change we have to compute for this, and therefore the gradient descent will make really work well, and will make some progress at every step. Okay, so the backpropagation algorithm may be used with other activation functions instead of logistic functions. Okay, so there are other, so this inventions or these experimentations are actually going on as we are talking, right? There are more newer activation functions people are experimenting with. One of the activation functions that come into play is the hyperbolic tangent function. This is tan h. Tan h is basically tan inverse h. This is tan inverse h. Tan inverse h is sine inverse h by cos inverse h. And if you compute that, it actually comes to this value. It actually comes to 2 of sigma, 2 of sigmoid, and 2z minus 1. Okay, so basically people have figured out that tan h also works really well, and there is something called Rayleigh function. Rayleigh function is something that we have studied earlier also, and is all actually used quite often, right? So the activation function is something which is applied after combining all the values from the input layer, and the activation function normally used is sigmoid as well as hyperbolic tangent function as well as Rayleigh. So basically, in uh, various kinds of problems, people iterate through these activation functions from time to time, and we'll actually go into more details now. So the hyperbolic tangent function also brings down the value between -1 to 1. Okay, so the idea is that every neuron should behave like something that brings something that generates a signal, something that generates like 0 and 1. That was the sole tendency of designing neurons. So the way, so basically neuron fires a signal, and signal has a certain value, right? So first attempt was that let signal only give the let each neuron give only 0 or 1. Okay, 0 or 1, right? So but that one was if we have like a very step function kind of model, that it gives 0 or 1, it is not differentiable, and we are not able to find out the gradient descent, right? Therefore that did not work. So other models like sigmoid function like this, or tangent like this, is used. Okay, so and the third function that is used is Rayleigh function. We'll talk about Rayleigh after the break. Okay, so let's take a break for 10 minutes. All right, so what we're going to do next is we're going to implement it in TensorFlow, as well as we are going to use an upfront library. And then what we're going to do is the next thing we're going to do is we're going to understand the hyperparameters, and afterwards we'll start the next chapter called training the neural network, the training model on the neural networks. All right, great. So okay, all right. So one of the things that is very important to know is that the we the neural networks perform really well if we put some kind of activation function, because they're able to then able to solve non-linear problems. Otherwise, they can't solve nonlinear problems. Okay, the one of the challenges with normal linear regression and other mechanisms was that they were not good for very complex problems, right? And that's where the neural network has been successful, where it has been able to solve most of the complex problems. And how it does that, it basically, one, it has multiple layers. Second, after each layer's computation in this, the model that we studied here, just after we are computing H1, so after H1, before sending the signal to O1, we apply the activation function. Okay, so one of the very important activation function is hyperbolic tangent function, 10H. Just like logistic function, it is S-shaped, continuous, and differentiable. But its output ranges from -1 to 1 instead of 0 to 1 as compared to the logistic function or sigmoid function. It tends to make layers output more or less normalized, and it is centered around 0 at the beginning of the training, right? It tends to make layers output more or less normalized. So you can see that it basically, most of the values of this, most of the outputs of 10H is 1 or -1. Only for small time it is like closer to the 0, right? So it is just like step function. In a step function, it is like like this. Okay, it is more or less like a step function, just that it is also differentiable and continuous. All right. Okay. A question from Shiva is, could you just do a recap of step function? Definitely. I'll just go over. Right. So this was the step function, whereby the step function's idea is this. Step function idea is, if z is lesser than 0, make it 0. If the value is greater than 1, make it greater than 0, make it 1. So the graph that comes out from step function is like okay, like this. Okay, so anything below 0, okay, is 0. Okay, anything above 0 is 1. Okay, this is step function. So the basically, whenever at every point wherever we were doing this, so just after we have finished the value here, we have finished the output here. Okay, h1. So on h1 we would apply this step function. So if the value is negative, we'll make it 1, or and so on. So basically that seemed to work like the neuron, and because neurons actually fire the signal, and therefore the decimal value was converted into 0 or 1. Okay, so basically it's like a harsh conversion of a decimal value into a continuous value into a discrete value of 0 and 1. Okay, or you can say Boolean value, conversion of a number into a Boolean value. Okay, that's what the core idea behind putting in the perceptron model. But in the perceptron model, they found that if we, after computing by multiplying weights to the inputs, if we put the step function, we will get the better results. So that was the core idea. Okay, so that was the core idea, and that could also be used in the classification. The activation functions are quite useful in the classification also, where you want to say yes or no as the output, and those are the meaning of activation functions. And step function is just one. Step function is one activation function whereby the value is either 0 or 1. Output is 0 or 1. Okay, but since the step function wasn't great for our approach to solve the problem is using the gradient descent. And since a rigid function like step function does not have any slope, okay, therefore the slope is always zero. The slope is always, yeah, zero. Therefore, it was decided to come to new functions like sigmoid. They performed really well. And then the other function after sigmoid, the other function, sigmoid or logistic. This is also called logistic. Okay. So sorry. So this function is also called logistic function, and we also call it sigmoid. And this function looks like, I mean, the logistic function also looks like this. And now so basically the hyperbolic tangent function helps speed up the conversions and so on. So I think, should I move ahead or should I explain the activation functions again? All right. Okay, great. Wonderful. So now the other activation function is actually really, really simple one. Okay, really simple one. It actually only cuts down the negative aspect of the value. If the value is negative, give out 0. Otherwise, give out the actual value itself. So this function is continuous if the value is greater than 0, uh, as well as lesser than 0. But this function, this function again is not differentiable, right? Below 0, it suddenly turns as negative. So we'll always have to put a condition saying if the value is greater than this, do return this, otherwise that, right? So the slope also changes abruptly, right? At this point, let's say the slope of the line is fixed, correct? And suddenly here, the slope of the line falls down to 0. Till this point, slope of the line is going good. And suddenly at this point, a fraction of change, a very tiny bit of change, the slope goes down drastically, abruptly. And that's the only problem with ReLU, but in practice it works very well and has the advantage of being very fast to compute. Okay, so this is the comparison of various activation functions. Okay, this is the step function. This is the step function that was the core of the MLP model, multi-layer perceptron. So this is the step function, but this is not used because of not be differentiable. This is 10H. This is 10H. Okay, 10H is also quite useful in it being used. This is logistic function. The logistic function varies between 0 and 1, while the 10H goes from -1 to 1. And this is the ReLU. You see here, like an elbow. So till here, the value is 0. And suddenly from here, it is basically the actual value. Okay, basically the actual value. So, all right. So the rate of change of these functions is actually very, it basically like this. So here, the step function, you see, step function is basically always the rate is 0. Okay, because it's always the elbow, right? The rate of change, there is no rate of change at any. If you vary here, the rate of change is 0. Rate of change of y with respect to x is 0. Similarly, rate of change is 0. Similarly, rate of change is 0. So therefore, the step function, the derivatives or differential of step function is always 0. And The logistic function that you see here, this one is still a normal curve, like a bell-shaped curve, while 10h, you can see that at 0, the at 0, the 10h, the derivative of the 10h has the maximum value and then comes down. So it's actually quite steep. The rate of change of 10h is quite steep. And while the value is, again, before 0, the rate of change was 0, right? And after 0, it is 1. Okay, so the dy by dx, the derivative of value is fixed like a step function. So you can see these are the various activation functions. We will use them whenever we'll discuss. We're going to discuss a little bit more about them ahead. So multi-layer perceptron is often used for classification, with each output corresponding to many different binary classes. For example, it's ham or spam, urgent or not urgent. So when the classes are exclusive, the output layer is typically modified by replacing individual activation function by a shared softmax function. Okay, so when we have at the rightmost layer, we want to, instead of predicting a value, we want to predict a particular label, meaning we want to do the multi-class classification, right? When we want to do classification, then what we do is, on the output layer, we have the classes, right? Each neuron on the output layer represents each class. Okay, and then we compare whether that output is matching with that class or not. Okay, so a question is, what is softmax? Yeah, that's what we are going to discuss, right? So what softmax does is, whatever value is coming there, it converts that into something between 0 and 1, and basically it converts the decimal numbers into probabilities, right? So basically what it does is, it brings it down between 0 and 1 and makes it such that the summation of all the values is 1. Okay, imagine that you had this output layer, right? You had this output layer, and this output layer belongs to, say, red color, yellow color, and blue color. And we got the outcome here. Output here that we are getting is here, from the previous layer, is like 5,000, and here, or let me just, yeah, let me just put it, say 40, and let's say zero point 0.1, right? It doesn't make sense. These values are not making sense, correct? Whether the image was, let's say we are doing image classification, and in the output layer, we have 3 neurons. And the value that it is getting here is, by summing up all the values, right? Okay, and all of that is, say, 500, just for the argument's sake. So let's say this is the value we are getting, or let me make it more practical. Okay, let me make it more practical. Let's say there is a value that is coming up here, and there is right. So, and there is one more neuron here. Okay, let's say there are decimal values that are coming in, and here at this point of time, let's say there is zero point 0.8, 0.9, and 0.95, right? Now, since we are classifying them into 3 separate classes, we don't want to have probabilities like this. We want to have probabilities which are summing up to 1. Okay, something between 0 and 1, and are summing up to 1. So what we do is, we compute, first of all, we compute exponential of every value, e to the power 0.8, e to the power 0.9, okay, and e to the power 0.95. Okay, and then what we do is, we divide, let's say we call it a, this is, let's say, a, b, and c. So we divide a by summation of all, a by total, and this is B by total, and C by total, right? Now, this is what this mechanism, this transformation is what the softmax is. So let's say the value was 0.8, so 0.9, 0.95. So what we do is we compute the e to the power of all of these. Then we compute e to the power, which is 0.8, e to the power 0.8 divided by summation of all of these. Summation of all of these. Okay, so that way, now you can see that if you sum up all these three, A, B, and C, A is e to the power 8, 0.8, B is 0.9, C is this. So we further, what we do is we translate this into normalized form. Okay, so you can see that all we did was we did e to the power that value and divided by this. Okay, that's what is normalization is. That's what is softmax. Okay, so basically, this ensures that the probabilities are the values are converted into something between 0 and 1, as well as the so we why we are doing e to the power something, so that the impact of individual decimal value is magnified, and that's why we are doing the e to the power x and then dividing by sigma. Okay, so when the classes are exclusive, the output layer is typically modified by replacing the individual activation function by softmax. Okay, so all softmax does is it is converting the values into something that looks like probabilities. All right, so I hope the example was clear to all of you, right? So the softmax function, because these are important parts, so please feel free to ask further questions. Even if you want me to explain some part again, I would love to do that, because these are the building blocks, and these building blocks are something that we are going to use again and again, right? That's why I wanted to go through the backpropagation in detail. Right. So the output of each neuron corresponds to the estimated probability of the corresponding class, right? And basically that's what softmax makes it happen, that it converts them into something that becomes like a probability. So that if you sum up all of these values, if you sum up all of these values here, the answer will be 1. Okay, so the signal flows only in one direction from inputs to the outputs. So this architecture is an example of a feed forward neural network, right? So we can do so what we are going to do next is we are going to do MNIST with our neural network. Okay, so that's why we are explaining to you the activation functions and softmax, and then basically we are going to create something called feed forward neural network, in which there is going to be input layer, there are going to be hidden layers, and they are going to be the output layer. On the output layer, we are going to put softmax, and then we are going to do something called, again, softmax. We are going to compute the error with respect to the actual values. Okay, all right, so the simplest way to train the neural network or the multi-level perceptron with TensorFlow is to use their high-level API called tf.learn, which is very similar to scikit-learn. The DNN classifier class is used to train the deep neural network with any number of hidden layers, and a softmax output layer to the output estimated class probabilities. Now let's take a look at this. So those who have not pulled the repository, please pull the repository. Okay, so I am in, let's say, CloudxLab my lab. And we click on Jupyter. New terminal. Okay, New terminal. Now what we are trying to do here is we are going to go to my ML folder and then deep learning folder and say git pull. All right, so it's up to date for me. Okay, in case there's a problem with your repository because you have made changes to the notebook, you can say git checkout and space dot. Okay, in case you have right, in case there's an error. So I generally prefer checking out individual file. Checking out means you basically revert the changes, your local changes. Okay. All right. So once I do that inside last modif, if you sort the data by last modified, okay, where did my ML folder go? Okay, here. Okay, now inside deep learning, okay, so we have the introduction to ANN. Okay, so anyway, this we have to run. Okay, this is what the perceptron model that we discussed. Okay, this was the classification that we did earlier on Iris and Setosa. So these are called activation functions. Again, whatever we were discussing earlier. So you can see this is called the logistic function. You can see logistic function, which is 1 by 1 to the power 1 by 1 plus e to the power z, right? And ReLU, you can see. And derivatives we have, right? So, right, this is how we compute the derivative. Remember earlier that we take a tiny bit of value, we add it with this value, subtract it, and compute the value, and this is what we did. Okay, now, all right, now this is okay, let me just run this part. Okay, now these were the activation functions that we tried to plot and demonstrate by actually computing them. Okay, we generated the value of z, and then we put the value of z in all of these functions, computed the value on the y-axis, and printed it. Okay, now this was sigmoid. This is sigmoid function. Okay, so if you see the sigmoid function and logistic function, see the difference? So let me show you. Where is the sigmoid function? Here, right? So you can see, is there a difference between sigmoid and logistic function? Anybody? Is there a difference between these two functions? No, right? They are the same, correct? So basically the sigmoid and logistic, we are going to use the interchangeably, and sigmoid is also called sigma, logistic is going to be used again. Okay, so that was the visualization of Heaviside and things like that. So, okay, now this is the important part. So first of all, let's try to use the out-of-the-box library of TensorFlow. called TFLearn. TFLearn essentially has coded everything for us, so we don't have to worry about it. And in most of the practical scenarios, you would like to use the out-of-the-box one. Okay, but that does not mean that we don't learn the underpinnings. And the objective of this class is to make to all of us learn what is going on, and we should not consider this as magic. We should know what is going on. All right, that's the core idea behind this course, that you should know what's going on instead of considering it that like black magic. Okay, so here we are saying that right here we are saying from the okay, so we are importing the input data from the MNIST example, right here from the MNIST package, and we are saying input data dot read dataset. So this is going to download and extract the dataset for us if it is there. If it is okay, okay. So basically, it is extracting and it has loaded our data in MNIST. We can take a look at what does this data look like. Okay, is everybody on the notebooks? Okay, so it is the dataset, and let's take a look at train. So train basically has this dataset. Okay, and right. So we could say dot images. Okay, you can see the dot images and dot labels. Okay, so basically uh, this data set has been loaded and it has all the values. Now let's define train and test. So this data set by TensorFlow provides the xtrain, xtest, ytrain, and ytest. Okay, so let's load those values. So now we have the training data, testing data, and training labels and testing labels. Okay, so we will basically train our model using training data and test using test data. Okay, now the next step is to just run the classifier. Let's just show you this. So import TensorFlow, then run the config, some random seed we are setting, and then we are saying infer real valued column from the input. So this is a utility function provided by the TFLearn. What it does is it only picks up the column which have the decimal values and ignores the non-decimal values. Okay. The next step is to right. Next step is to call the DNN classifier. Okay. So here we are basically calling the classifier. You can see there are two layers, one with 100 neurons, second with another 100 neurons. Number of classes are 10, and feature columns are equal to feature, right? The columns that we have extracted, the real value one, and we are passing the config object. And then we are saying this is kind of telling the TensorFlow that we want the we want it to be scikit-learn compatible. So it's kind of a wrapper. This is kind of a wrapper over the TensorFlow class. Next is we are just calling just like scikit-learn. We are saying this classifier dot fit. So this basically will basically train the neural network. So let it be trained. So it is going to take some time. Okay. So how many steps? Okay. Yeah, it is going to go up to 40,000 steps. So it's going to take quite much of time. Okay. So here it's basically training it, still training it. Okay. Are you guys also running it? Balaji, Bintao, Gigi, James, Pavan, Pratik, Ross, and Shiva. On which host are you? I am on E. Here you can see Jupyter.e. So those who are on E basically will, right. Shiva is an E, okay. Gigi is also on E, okay. Then it's going to be really slow. Okay, Vidya is an F. No, that's okay. Let it run. Okay. Looks like the distribution is not uniform, probably because of mine. And since mine was only on E. Okay. Okay. All right. So Pavan, Balaji, Gigi, Shiva, and me. Wow. Most of us are on E. No wonder. Okay, we are about to finish. Right. So question from Binta is that what are hidden units? Okay. Hidden units basically this. Input and output is anyway have to be done, right? So the layer between O and input and output. This is the okay. These are called hidden units. Or in this case, you can see this is a hidden unit. Okay. So we are saying that as by the way of this diagram here, we are saying that we're going to go with 100 units of two hidden layers. Okay. So both the hidden layers are going to have 100 each neurons. Okay. So, all right. So it has finished the computing. The loss in the final step is really, really low. So now let's see how the prediction looks like. So So you can see that the accuracy is 98%. Accuracy is 98%, which is actually really, really good. Which is actually really, really good, which means that it is performing equal to probably better than human eye. Okay, it's performing better than human eye. So you can see that it is far better than our linear classification or other classifications that we learned in the first part. So on the MNIST data, on the nonlinear data, it was able to perform really marvelous. Okay, so so now we will try to create the same thing by ourselves. We will try to create the same neural network by ourselves and use backpropagation to solve it and then see if we are able to achieve a similar performance. Okay. Yeah. A question from Shiva is that the output value I see is slightly different. That's right. Because of the random values, that random initialization values. Okay. Therefore, the output will be slightly different. All right. So, okay. So this is very impressive that it is able to do the accuracy of 98.07. How much is your accuracy? Okay. For me, it is 98.07%. Okay. Right. Okay, so we can actually, we can actually try increasing the hidden units if we increase both them by say 50 each, right? Number of classes is 10 because we are classifying them into 0 to 9, 0 to 9, right? So that therefore, great. So, okay, that's a good point. Okay. Are we checkpointing it anywhere? No, actually, this is a temporary folder. Okay. So could anybody confirm that are you having the same folder? It's a good point. No, actually, the Abhinav's question is that it is being saved in the temporary. That's correct. But here it's different, right? Correct. ZZ's is different. Therefore, the accuracy will be different. All right, but good observation. All right, so all right now. Okay, good question from Pavan. Pavan's question is there any way to check where are the 2% data where it was not accurate? Yes, you can check. Use the standard predict like this. Okay, you could predict on this. So you have got predictions. Now using the mechanism, right? The one that we did earlier. So if you take a look at, say, predicted values, right? Okay, so what we could do is take these predicted value and the actual class, this one, and then find out the places where the image is not matching, where the y predict and y test is not equal. Okay, take those cases and look at those images. Look at those images and you'll get the idea. Using the mechanism that we did earlier, whereby we basically plotted the image on the matplot, right? So we could do that. We could do that, and thereby we can figure it out. All right, wonderful set of questions. So, okay, matrix subtraction would work. Yes. So let's say here we could actually this is y test, right? So this is how it looks like y test and y predicted. So we could actually do y test, y predicted. Okay. Or y predicted dot classes. Okay, and we could do so here you could actually do array. Okay, and yeah, better idea would be to to have the index actually. Okay, to have the index, so we could say I equals 0 and for j in a, if I equals true, okay, print I. Okay, so oh, why didn't it do j? Okay, so we could also do this way, where these values are equal. Oh, we have to increase this. So these are the values for which it is giving errors. Okay, these are the index. So you could, let's say, take a look at this. And what was the name of the X test, right? X test. So you could say X test. So we could basically plot this particular image. Okay, we could actually plot this particular, let's say this particular image, we could actually plot. We could actually plot this particular image. Okay, okay. So using the, I think I'll have to pick up the value of that one. So this one is one such image. Do you guys remember how did we plotted that image earlier? I'm actually curious myself to figure out if right, in the classification we did MNIST, right? I actually want to see that how does this image look like that it could not classify. Okay, let's see if I'm able to do that in the class. Okay, I hope it's not too boring a thing. Okay, all right, this is how we did, correct? All right, so I'm going to just create this part and just take this image. Okay, all right. So it could not uh, predict it. So we can actually print here the predicted class also. Okay, predicted. Predicted was what? Predicted was say y underscore test. This was right. So this was print here. You could say print predicted was something else, not this. Okay, so you could also give it a try with me. These are the things that make you familiar with what we are doing. If you don't touch and tweak, right, you won't get familiar. Therefore, it's important to tweak everything, whatever we are working on that. Okay, so we can just do a break here. That's all. All right. Okay. So predicted was actual was 4 and predicted was 9. Okay. And so this value is being predicted as 9 instead of 4. Okay. It's not wrong actually, right? Basically, it's considering this to be like 9. All right. So, okay, no wonder maybe the way mostly 4 has been written is actually like this. Okay, so it's not the fault of the network actually. The data is also, so the way we generally write 4 is like this in this data. The 4 like this is very rare, or 4 like this is very rare. Okay, so it's doing pretty good. You can see that. All right, so if we don't break here and okay, so we could actually take a look at, say, in case of 24. All right, so I can actually print it, something like this. Okay, so in the second case, in this case, the diagram looks like, okay. So in this case, what's happening is, in this case, predicted was 2 and actual was 4. Oh, for some reason it is predicting this as 2, okay, instead of 4. All right, so you can take a look at this. So should I commit this particular code? Okay. Okay. Display images and git push. All right. So yes, we were successfully able to take a look at these images, and okay. So that was a quick discussion on the all right. So far we've just used an existing library of TensorFlow, a little higher level library, just to do the predictions. Okay, just to do the predictions, and we were able to do that successfully. Now, great. So, okay, so everybody is clear about it. There was one question I missed. There was a question from, yeah. Okay, so I think I was able to answer Pawan's question. Is there any way to check with the 2% data where it was not accurate? Okay, and a question from Bintao is that, does accuracy score means accuracy here? That's correct. That's correct. This is basically the accuracy. Okay, so yeah. Let me also hide this portion. You can always press control. Sorry, you could just go between the editing mode and command mode in Jupyter by pressing escape. Okay. And if you press enter, you will go back to editing mode. If you press escape, you will go to the command mode. And if you're in command mode, you can press the commands. Like, for example, I want to hide this output. I can press O and it will hide the output like this. Okay. So that we, right, we can scan through the data, scan through the notebook. All right. So next question was, Abhishek's question was, should not it be xtrain 115? That's correct. So no, actually we were testing on, because we are running it on these comparisons right here on the test, correct? That's why. That's why, because this 98% is basically based on the test data set. All right. Good question. Now moving ahead. All right. So far we have basically used the out of the box library. Again, here we are saying there are two hidden layers, two hidden as in the layers other than input and output. Okay, because if there is because input and output are not basically somewhere we put the weights. So we have two hidden layers. Number of classes are 10. Okay, number of classes are 10. The feature columns are basically here the feature columns are mm, the one that we want to feed. We want to inform TFLN that, hey, we only want to process these columns, not all the columns. Okay, and then while fitting, we are saying that batch size is 50. Batch size is 50. What does it mean? That every time we are training our we are training our neural network, we are giving 50 records, and then we seeing the output, then again giving 50 records, and so on. So we are basically doing the training in 50 batch size. Okay. So if right, so basically every time we are feeding in the data to the network is 50 records. Okay, if we increase the batch size, the memory might overflow because the entire like all the instances, whatever computation we did for single instance in this here we did the computation for single instance, but for if there are many instances, it'll do the simultaneous calculation of all of those, and therefore it will overflow in case there are batch size is really huge. Number of steps, as in number of steps for which to train the model. Okay, if we pass none, that means it will train forever and will only stop when the error is increasing. Okay, so no, it'll actually run forever. You'll have to try it out. Okay, now. Okay, so we have already done this part. Okay, also we have we defined these data sets. So I think we have already gone through. Okay, so let me take a look back. Yeah, I think we defined this part. So all we did was we defined the data types and the variables. Then we've already gone through this part. Any questions on this? I can clarify. There is a question from Pavan. Question is how to get all options methods after entering the operator. You can always press dot. Okay, you can always press dot. Let's say I want to find out what are the methods in say sklearn matrix. Okay, what are the methods there? Okay, all right, no. Okay, it'll be like from this import. Yeah, I've just pressed the tab. You can press the tab and see. Okay. Similarly, if I want to find out what are the methods available, I could press tab. So using tab, you can get them. All right, great question. So now, so we basically ran this part, okay, and we also ran this and saw that accuracy was 98.25. And so under the hood, the DNN classifier creates all the neuron layers for you, and it uses by default the ReLU activation function. And we can change that by changing the activation function parameter. The output layer relies on softmax function, and we'll talk about these two parts. So the output layer relies on the softmax function. All it does is first it converts the input values into probabilities, and then cost function is cross entropy. Cross entropy is what we studied in case of classification. Basically, cross entropy means it compares the values of predicted and the actual, and based on that, it does the score. Okay, so if the cost function is going to be more, means that the cost function is 0, that means we are good. If the cost function is not 0, that means it's not right. Okay, so the cost function that we're going to talk in a while. So the TF-learns library was quite new earlier, but now it seems to be stable and quite usable, and will evolve on the time. Now, let's start with training deep neural network using plain TensorFlow. Okay, so TensorFlow's lower level Python API provides more control over the architecture of the network. All right. So TensorFlow gives you the entire control of creating anything. If you don't like existing neural network, you can actually create your own. And it's not necessary that you only use this new kind of neural network. You can entirely create your own. So TensorFlow is really lower level API with which you can design things which are algebraic in nature, which are algebraic or which requires like evaluation of expressions, feeding the values, and so on. So you can create those kind of values using TensorFlow's lower level Python API. So in this section, we will build the same model as before, the MNIST model, using TensorFlow's lower level Python API, and we will implement the mini batch gradient descent to train it on MNIST. All right. So question from Binta is, how does output layer relies on softmax functions? So basically whatever input it gets, okay, let's say at this point it's getting some values, it'll convert them into using softmax function, it'll basically convert them into probabilities. And using those probabilities, we compare that, okay, here at this point, we are getting this much probability of this class. So we'll compare that with the original one. If the class is same, you'll get the good result. If class is not same, then you'll get the penalty. So that's what we will do. Okay. So soft layer basically is using the softmax layer. The output layer is actually using the softmax function to convert the input numbers into probabilities. All right. Basically, the way we convert the values into by normalizing, right? By dividing by sum of all the values. The same thing is done by softmax, just that it first converts each of the value into e to the power something, right? So it computes the exponents. All right. So okay. So we are going to the question from Binta Fardari, the softmax function may rely on the output layer. Not really. Actually, the word rely is a misleading word here. So softmax function is being used by the output layer. You can say that. At the output layer, we basically, whatever input it's getting, it's converting that into probabilities. Okay. That's all. So if we have, let's say, an output layer, like, okay, let's say we have an output layer. Okay, so let's say this is our output layer. The values are coming in, right? So here it might choose to, okay, it might basically convert this value, let's say 0.8, say 9, and 0.99, right? So it might convert first into e to the power something. So let me just show you. Let's say a, and let's say import numpy as np, and a equals numpy dot exp. Okay, and the first value was 0.8, right? 0.8. Correct. And the b would be np dot e to the power xp. Second value was 0.9. Okay. C is equals to np dot exp, and the value was 0.99. Okay. So now it'll basically convert this into, so you can see A is this, B is this, and C is this. Okay. Now we'll say, what is the sum? Sum equals to A plus B plus C, right? Now the new values of these is A by sum Okay, and this is 0.3. So this gets converted into 0.3, right? And the B21, right? So B by S is 0.33, okay, and C is how much? 0.36. Why did we make this mistake? There is C, okay. So there's, did we make a mistake somewhere? So we have A, all right. So if we have like this, 0.3, 0.33, not 0.3, 0.8, 0.8, 0.9, 0.99, right? Okay, so we are saying np.exp of A. Okay, so let's call it E, right? So we have this E, and summation of E is how much? 2.69, okay. That's our sum. So we have E and we have S. If I say E by S, now it makes sense, right? So now the probabilities look like this. No, it doesn't. Does it make sense? No. So summation is 2.6. Okay, this is okay. This is actually closer to 1 and there is a decimal error. Yeah, you're right. So it is supposed to be this. Thank you so much, Bintao. All right, now it makes more sense. So you can see, actually earlier were also correct. See, 3, 3. Oh, we were not counting properly. So 3.3 is 6 and 3. And so this is actually, the summation of all of these is actually close to 1. Okay, the summation of all of this is close to 1. All right, so basically this is what the output layer is doing. Output layer, whatever value it's receiving, it's converting into these probabilities. And then these probabilities are compared against the probability of the predicted value. This is y predicted, right? And this is the y actual, okay? In y actual, it could be 0.1 or so. Okay, so that's what this is what softmax function is doing. All right. Now, does it make sense to you? Okay, great, great. I think the first calculation was itself right. Okay, but anyway, you could also see that this life is made so simple with NumPy and using the vectors instead of each individual variables. All right, so now, so we will implement gradient descent to train the MNIST dataset, and we will use the TensorFlow's low-level API to get the work done. Okay, if we are using some API, we should know actually that how it's doing the things under the hood. So the following steps will be involved. The first step is construction phase. We will create the TensorFlow graph. Second step is execution phase, when we actually run the graph to train the model, right? So here is the checklist for our code of the construction phase. We will design the neural network, the entire model, define the cost function, then we will do the gradient descent optimizer, that will tweak the model parameters or the weights and minimize the cost function or loss function. And then we'll specify how to evaluate the model, create a node to initialize all the variables, and create saver for to save our training model. Okay, so we'll specify how to evaluate a model, create a node to initialize all the variables, and so on. All right, so let's get started. So first we need to import the TensorFlow library, and then we must specify the number of inputs and outputs. And then set the number of hidden. Basically, we are defining these variables. Okay, we are saying our total number of inputs are going to be 28 by 28 because that's what our input data is. Our MNIST data has images which has, each image has dimensions equal to the number of pixels, which is 28 by 28. Number of hidden layers, right now here we are saying that, sorry, there are two hidden layers, hidden layer 1 and 2. The first hidden layer, we are going to have 300 neurons and 100 neurons in the second layer. Okay, and the number of outputs is 10. Why? Why do we have number of outputs as 10? Because that's the total number of values in y. Okay, total number of values in y, 0 to 9. The predicted label is, the total number of labels are 10. Okay, so now let's go back to here the neural network, the notebook. So let's try to run it. Okay, so let's first of all define these values. So this is, I hope, clear to you. Now, the next thing is, instead of feeding data now or defining X and Y, we are just defining them as the placeholder. So capital X and small y are the placeholder, right? Capital X has, we have not defining the total number of rows because we don't know that. The total number of rows could vary, and number of columns in this capital X is equal to number of inputs, which is 28 by 28. That those are the total number of pixels, okay, in each image. So the capital X has these many rows, which is infinite, and the number of pixels equal to the number of pixels, the column. Okay, wonderful. Now we have okay, a question from Indao is how to choose number of hidden layer and number of neurons in each of them. Really hard question. So I think that's the whole idea about right, the whole machine learning research basically is about them. So we are going to go into more details about that part again just after this. That's what we want to spend some time. Okay, and basically when we say hyperparameter optimization, that's what it means, that how to choose the number of layers and number of neurons in each of them. Good, good. So we will keep this question. It's good that you asked, and we'll keep this question towards this end of this. Mm, uh, just after this, just after we finish the TensorFlow, we're going to do the parameter optimization, and then we land that. Great. So what we learned was here, right? So we have created X and Y as placeholders, and here we are defining a function for creating the layers of our DNN. So sorry. Okay. Now this function is a generic function. Remember in a last session which we discussed how to create your own function to create layer or ReLU, right? So it's the same function. We are defining our own function, which takes capital X, number of neurons, meaning it takes the input layer and it takes the number of neurons in the current layer, and then name of the current layer, and then it creates that layer. Okay, so for this scope, we are creating the number of inputs. Here you can see it's an empty array, so number of inputs, yeah. Then we are creating the standard deviations. Okay, of 2 by under root n. We will talk about why this is 2 by under root n. Okay, and then we are computing the normal. Basically, what is it that we are trying to do here? We are trying to initialize the weights. Initialize the weight. Remember that when we talked about our model, we were basically picking the random values of weights. For the example sake, we took 1, 2, 3, 4. But in in real life, this value of weights is actually the decimal numbers, and these are chosen very carefully, so that we basically start with the we have a good start. Therefore, here we are kind of creating these random weights between 0 and 1, and so many of those. And we are saying that use the standard deviation mechanism. Use this mechanism to do that. We'll talk about this particular cryptic logic here. Okay, so we are saying that the standard deviation of values must be 2 by root of total number of inputs. Okay, so the standard deviation should not go beyond this, and in this range, from 0 standard deviation to this range, we must create the weight value of weights. Okay. Now, once we have this is basically these are random variables, and we are just choosing the range for them. Okay. So here, the name is kernel. Kernel here, basically, we are giving W as the name for we are giving name called kernel to this, bias to this, and this name is generic. This name is generic in the sense that this name, whatever name we are passing, it will create the layer. This is the name of the layer. This is the name for the weights, and this is the name for the biases. We are just giving them name so that when we display them in our TensorFlow graph, they will look really nice. If you have created 5 layers, so there will be 5 names in the graph, and those will be displayed independently. So every time you call a neuron layer, it's going to create a layer of this name with whatever name you're calling it, and with these many neurons, and the input to this layer will be this, and it'll return the output, the output values, okay, which you can tie it again. So once you have defined this function neuron layer, you can use that to create your a layer like this. You could say tf.name.scope, and then here we are saying creating another name or scope, and then in here we are calling the same function 3 times. First time we are calling it with the input, right? So we are basically creating the input layer here by passing it this, and then we are creating the hidden layer by passing the input layer. Input layer we have already created as X, capital X here. So we are creating a layer with the name hidden. So this is the first hidden layer, this is the second hidden layer, this is the output layer. Okay, this is the output layer, and here the input to this particular layer is these capital X, which is the input layer, and whatever is returned from it, returned from the first call, is actually the input to the second layer, and whatever is the output of the second layer is the input to the third layer. Okay, so we are basically stitching them around. Okay, so we basically created say this is our X, right? This is X, and this is the first hidden layer. This is first hidden layer. Okay, and the input to this hidden layer is X, coming from X, and this input to the second hidden layer, this is second hidden layer, goes from here, and then we have the output layer or logits layer, and this way. This is what we are trying to do. Inside each hidden layer, we have basically neurons. Okay, we have basically the neurons. Here, these are input neurons, and so on. All right. So essentially, this is what we are trying to achieve. Okay. Then we can right. Then we'll talk about how we can utilize the internal methods to do the similar things, as well as how to do the hyperparameter optimizations and multiple other things. So we'll continue from here tomorrow, and I think tomorrow we will basically start from here and go to the till the vanishing gradients. Okay, and so that's pretty much for today. So any questions? So all we are trying to do is whatever we did earlier, right? To create a function to create the graph. In the same way, we are using this. We're creating our own function. There is a parallel function in TensorFlow called dense that creates the whole layer. All right. So that's pretty much for today. Any questions? Balaji, Bintao, Gigi, James, Pavan, Pratik, and Shiva. What is the difference between W and name kernel here? Basically, it's the same thing. Okay. All right. Wonderful. Great to have you in the session. Wonderful set of questions. Thank you, everyone. I look forward to see you tomorrow.